Martin Panevsky. I manage the embedded avionics lab at the Aerospace Corporation, and I'll be talking about some new developments, some new simulation systems that we've built recently there using FPGAs. First, just a summary. I'll introduce you to some of the type of simulations that Aerospace does for IV&V of flight software and flight computers, why there is a need to move to a more COTS-oriented systems that are more flexible, easier to build, and we'll talk about a little bit about the FPGA technology that allows us to do that, and then I'll conclude with where we're going from here. Now, there are two types when we do IV&V at Aerospace for flight software. There are basically two types of simulations that we do. One is the what we call software scientific simulation, where you are running the actual flight code, but it's compiled on a workstation of your choice, on a scientific workstation that allows you to run faster than real time. And then to close the loop on the flight software, you have a dynamic simulation on the other side, which actually could be running on the same workstation, which is a physical representation of the system that you are simulating, a launch vehicle, a spacecraft, or what have you. That closes the loop and allows you to run the flight code in flight mode. When you do scientific simulation, a software simulation, there are advantages. It's faster than real time, and there are disadvantages because these simulations are typically single-threaded. Real hardware doesn't work like that. You're not running on the flight processor. That's another drawback. You lose a lot of the timing. Well, you lose all of the timing. All of the redundancy if you have multiple lanes on a scientific simulation. So basically, what we use scientific simulations for is a pathfinder to the real test like you fly system, and that's a HIL, a hardware in the loop simulation. And what we do there is we essentially rebuild the flight computer in the lab, and we build it in a way where we are going to use the same processors, the same interfaces that are used on the vehicle. And that allows us to run the actual binary machine code with no modifications. And again, we close the loop on the flight code with a dynamic simulation. Now, and that's great. It works very well. And I will show you later on a little bit how we use these systems to stress the flight code and to find certain, to find bugs. We essentially try to break it. And these systems work very well for that purpose. The problem is that they're expensive to build. They take a long time to build and integrate. And so we're looking for a more cost-effective approach. And using FPGA technology, COTS technology, in this case, this is National Instruments Flex Rio FPGA card, is we feel the way to go. And we'll get into that. I'm not going to talk about what FPGAs are because I'm sure you know what they are. This chart was easier to clear that way. It was for a different audience. But I'm sure you know what FPGAs are. So here is a legacy system. This is how things used to be done. This is a hardware in the loop system for an existing space vehicle. And it's flight equivalent, which means that it's using the exact same processors that are used on the real thing. It's using the same interfaces, communications buses, everything that's on the space vehicle. So essentially, this is the lab representation of the flight computer and the flight avionics. Like I mentioned, some drawbacks of that is that it's costly, it's difficult to build, it's even more difficult to integrate and run. And you also have, especially for systems and programs that you're supporting for a long time, you get into the domain of parts not being available anymore, certain pieces of hardware, if they break, you cannot replace them. But really the main driving factor is the cost and the flexibility. Although these systems work very well for what they're designed to do, they're not very flexible because it's all custom hardware. So it works great for a specific program, and that's it. You cannot use it for something else. So with the FPGA approach, we feel that we can reduce the cost, make it more flexible, because as you know, FPGAs can be reprogrammed. And also it will offer a lower entry point for smaller programs that might not be able to afford something like this. So this is a typical flight computer, or typical hardware in the loop simulation, where this thing here is the flight computer, and this is the dynamic simulation. So we have a dynamic simulation, which is essentially pretending to be the vehicle. It's outputting sensor data to the flight computer. Then you have one piece of the flight computer which is running the IMS code, the internal measurement system code. It's processing essentially gyro data. And once that code is processed, it's sending it over to the other piece of the flight computer, which is actually running the flight code. Once the flight code is running, it's executing its guidance algorithms, its state machine, and at the end of every execution cycle, it's outputting commands back to the vehicle, which in this case is just the workstation. Of course, the flight code doesn't know that it's running that it's talking to a workstation. It thinks it's in a flight mode, so it's doing everything as it would happen in real flight. It's outputting telemetry, it's doing fault management, and everything you want to see happen correctly. So that's how it works. Now, what we've done here is keep in mind that these are the actual CPUs that will be used in space, and the correct or very similar I/O cards and devices. What we've done, we have retained the original CPUs. So basically, from the old system that you saw, the only thing remaining are the CPUs, because there is no reason to emulate a CPU. That's very difficult to do, and it doesn't really get you anything. And these CPUs are generally available, so you just might as well get one. So the CPUs are still the correct original CPUs, but we have replaced everything else with FPGAs. So all the I/O interfaces and cards, all this custom hardware has been replaced by FPGAs. So that's the new system. Now, let's see. Okay, like I mentioned, we have replaced all the I/O cards with FPGAs. The VHDL code that programs these FPGAs were developed independently at Aerospace, so we have total visibility to it. We can change if we have to. Now, how we did this? We basically took the spec for the system that we're trying to emulate, and we coded the FPGAs to that spec. And then we integrated the system. It's a little more complicated than that, but basically that's the idea. And again, the FPGAs now are performing all the usual functions that used to be performed on custom hardware. All the interrupts and voting logic if you have, and sensor FIFOs, and dual port RAMs, and everything you need is now on the FPGAs. And this is now an operational system. It's not a concept. We built it, we validated it, it works. We're actually using it for mission support. So on top of being flexible and modern and a lot cheaper, this new approach gives us additional capabilities that you don't get in a legacy hill. Typically what you're trying to do, you're trying to break the system. And there are two ways to break the system. The flight code might fail, or the hardware might fail. So if you want to fail the flight code, well, that's easy to do. But if you want to simulate an avionics failure, then it becomes more difficult because on a legacy system, which costs millions of dollars, you're not going to break anything. But in an FPGA system, you can easily break it because all you have to do is corrupt the firmware on the FPGAs, and then you can emulate door memory failure, red hits, sensor failures, basically anything you want. And of course, if you then have to provide mission support the next day, you reload the correct firmware and you're ready to go. Okay. Also, you have additional capabilities. I've been sitting here for 2 days listening to people talking about debugging and how difficult it is. And yes, it is very difficult when you're dealing with hardware. And one thing that the FPGA-based approach allows you to do is the FPGA can actually do a lot more than what is required from the ICD document. It can do additional debugging and data logging on the fly for you, and we've done that. So when there is a problem with the system, especially at the beginning when we were integrating, there were a lot of problems. We would look at this data log file, which we designed to be able to record and then output somewhere to disk every single transaction on the backplane, on the bus. So then we go to that file and we look to see what happened. Should I wait?
No, I muted him. Go ahead.
Okay. So we go back to that file, we look at what happened, and being that every single transaction is recorded, it becomes very easy to see when something is out of the order and what happened. So you would be able to say, oh, I see this interrupt happen because this was hung up and that shouldn't happen. Okay, we need to fix something. Instead of just blindly trying to guess where the problem might be, because you cannot catch anything like that on a logic analyzer. The logic analyzer only has memory for a few seconds. And if this bug that you're chasing happens once a week, then you won't be able to catch it on a logic analyzer. So another thing that this approach will allow us to do is to move our efforts towards the left-hand side of the engineering V that you've already seen, I think, yesterday. Typically, when you're building a hardware emulation of the flight computer, you wait until the system is more or less complete. So you start your work somewhere around here. Well, so that means you're already late. What we would like to do is start doing our IV&V early in the game, and that means somewhere here, when the contractor is still very fluid in their design. And with the FPGAs, we can do that because as the system is maturing and changing, we can change with it because the FPGA approach makes us flexible. As long as they don't change the processors, which they won't once they've picked them, we can accommodate pretty much any reasonable change. So the bottom line is we get involved into the IV&V process much earlier. Where are we going with that? So the system I showed you is not that. The system I showed you is done. It works. It was done with low-level VHDL code, and that was a great improvement. But the next step we're making is going towards this, which is the National Instruments LabVIEW FPGA paradigm, which we think is very well suited for what we are trying to do here. Everybody knows LabVIEW or National Instruments, and they have FPGA cards. They have more than 500 various cards, hardware cards. So pretty much anything we need to build a hill, they have it. So we don't have to design it. We can just buy it, and it's fairly inexpensive. They have very large FPGA cards that are now Vertex 5, and I think soon they're coming with Vertex 7, which is so large that you can fit, well, a lot. Let's just say that on a Vertex 7. And it's all integrated into a COTS inexpensive chassis, and it's also under the LabVIEW paradigm. So you can program in LabVIEW, and the part of the LabVIEW code that works on normal hardware, so to speak, is just LabVIEW. And the part of your LabVIEW code that needs to run on an FPGA card gets compiled by LabVIEW for you. So it's all done and nicely integrated. So for a new project that we're working on, this is the approach we're taking. There was somewhere a mention that the system I showed you before is producing telemetry which is close to the telemetry from the real vehicle. That was actually an understatement. It's actually producing telemetry that's identical to flight telemetry. So I was just being, we were just being cautious at our statements early on. So this is kind of a trade study slide as to the three different types of hardware-in-the-loop systems that you could have. One is custom hardware, which is the legacy approach I showed you. This one here in the middle is the FPGA approach that I've been talking about. The third one is the essentially an engineering unit, design unit from the contractor. And advantages and drawbacks. The custom one is costly, takes a very long time to get into operation, and you essentially have to build the system yourself, so you get a lot of insight. The FPGA-based approach is a lot faster in our experience, and immeasurably cheaper, and you get even more insight because you have to actually code the FPGA from their ICD document. So you are really rebuilding the system. The third approach, where the contractor gives you a flight computer to play with, you're saving a lot of time, but these things usually are very expensive, and you get minimal insight because essentially you're presented with a black box that you are not allowed to and you wouldn't want to break, and is what it is. So very minimal insight, and the whole purpose of having this is to have insight so that you can do IV&V. So we feel that the FPGA COTS approach is the best approach right now. So again, in conclusion, we feel this is a way to reduce cost, make the hardware-in-the-loops IV&V more affordable to smaller programs that might otherwise be unwilling to or unable to pay, and allows us to get into the IV&V game early into the process, which we call on the left-hand side of the engineering V. And especially with the National Instruments approach, we could essentially reuse this chassis. We can reuse this rack fairly easily for a different program. So we don't have to buy everything from scratch and redesign it. We have to unplug a few cards, maybe plug in a few additional cards, and we can start integrating a completely different program. That's what I have.
Questions?
Do you consider maybe going one more step further and substituting GPUs for FPGAs?
GPUs for FPGAs? No. GPUs.
Well, some of the customers I support, without naming them, I'm starting to see on the embedded side, non-space, they're going from FPGAs, which we know aren't exactly cheap, especially if they're the way hard in space they're not. But they're going to look at using GPUs literally going off the shelf down at Best Buy, and it's running the same software. It's longer to get your machine live than it did convert the software over. They're getting the same bang for the buck with FPGAs.
So the question is, are we thinking about replacing FPGAs with GPUs? Right. My feeling, we are using GPUs in the lab, but for a completely different purpose. We're using GPUs for number crunching. When I wanted to build a supercomputer on my desk, I used a GPU. The way I see this is you are replacing, let's say, an existing board that you don't want to rebuild, you want to code its functionality in an FPGA. The FPGA is I feel, the natural environment to do that, because you're replacing maybe 100 different ASICs with one single FPGA chip. And what you want is to emulate the timing picture of these 100 ASICs, and they are running in parallel. And the FPGA is the only one that can run truly in parallel at the same time. Now, if you have a GPU, it can have hundreds of cores, but and they could potentially, each core can do the functionality of 100 different ASICs, but inside the core, the operation is still sequential, where in the ASIC and in nature, everything happens at the same time. So we feel that as far as timing is concerned, and timing for these systems, especially if you have a multi-lane system that needs to, where the different lanes need to talk to each other to make sure that each one is healthy. Timing is everything. So, yeah, yes and no. I don't know if I answered your question.
Answered perfectly.
Yes.
So you guys went to the NI. So you guys went the NI way, and the NI led you FPGA chassis.
Right.
How much you have an insight into the IPs that we provided to you, and the total, probably like
The IP?
both the IP
Uh-huh.
and the automatic Verlag.
Right. Okay. The question is, when I'm compiling with LabVIEW, how much insight do we have into what's actually produced as far as the layout on the chip? And the answer is none. But that goes for everything, because if you in the Pathfinder system that I showed you, where we actually coded low-level VHDL code without using NI, once you have your VHDL code, then you're at the mercy of the Xilinx tool set, or whatever you're using. You have no control how that compiler works. You give the Xilinx tool your VHDL code, and then the way you get the bit file is you have no control over that. You cannot, I don't think anybody would go in when you have millions of cells and start doing routing by hand. I mean, the only thing you can do is verify that the timing constraints are satisfied, and that's it. So the same thing goes when you're doing with LabVIEW. You start from, let's say, the ICD document, and you say, okay, I want these FPGAs to do this and this and this in this much time. You code it up in LabVIEW, and then you say, okay, go. And what gets loaded on the actual bit file is something that, then you can run a simulation, of course, and you can verify that your timing and then your functionality is satisfied, but that's all you can do. So it's like running a compiler on your C code. Do you know what the compiler is really doing? No. You just assume that the binary that comes out will work. It's the same. It's the same problem. Okay. Yeah.
Tunable, like when that interface is tunable, for example, it's giving you a bit code, etc. Can you do that interface for various parameters?
The interface between the LabVIEW cards and the CPUs?
Like, a compiler, you can do the compiler for performance, for size.
There are some configuration flags, yes. Not a whole lot, but there are some. And it's mostly the way you actually, the real configuration is in your LabVIEW code. when you want to accomplish something in LabVIEW in general, or in LabVIEW that will be loaded on an FPGA, there are many different ways to do that. And based on the way you choose to do it, it will give you a different bit file. So if you know what you're after, you can kind of tailor your coding approach at a higher level. Okay.
Any other questions? Oh wow, look at that.
Yeah. Yeah.
How dynamic is your fault injection? Can you inject faults during runtime through some external interface, or is it a little pre-canned beforehand?
There are many different ways to do it. If you want to simulate that something happened in your space environment or something happened to your space vehicle, then it's easy because all you got to do is inject that fault into your dynamic simulation. And there are various ways to do it. You can do it in real time, you can do it at certain time, whatever you want. If you want to do it on the avionics side, then the answer is you can do it both ways. In the FPGA environment, you can program the FPGA to, I mean, for instance, let's say you want to inject a fault at a certain time in the FPGA. Well, you can easily program a counter in the firmware that counts to the time you want. And when that time happens, boom, something else happens. So in this way, you're just sitting there watching it. You don't have to really go interactively. Although you can stop it, you know, essentially hold the system, go and tweak something in memory, or change some register, and then continue. So you can do it both ways. Yeah.
In the replacement diagram of the keep the CPU in there but replace the I/O.
Yeah.
The processors we heard in the last 2 days have like spacebar and 5053 on it. For that stuff, are you interfacing to that electrically, or are you just tapping into the flight software that's putting data on those buses and representing it in the FPGA?
Let me see. So the question is how we're actually talking to the 1553 bus?
Well, if the unit under test is the flight software running on the CPU, how
Right.
are you electrically connecting that for cases of data buses like spacebar and 1553?
In the Pathfinder project that I showed you, the CPU actually has a built-in 1553 interface. So we didn't have to mess with that too much.
So you just directly connected that to your models and didn't necessarily go through the API?
Right. Yeah. In the case of LabVIEW, they do sell a 1553 Pixie card, which has LabVIEW driver. So once you plug it into the chassis, it knows it's there and you can talk to it on the bus. Okay.
Thank you very much.